So example 6.2.2, using the empirical rule. So the mean and standard deviation in months for the age when a child first starts walking are about 15 months and 3 months respectively. And we're told to assume that the distribution is normal. Okay, so that doesn't mean normal versus abnormal. That means a normal distribution curve when we're talking about normal in statistics. So part A asks us to identify the individual, the variable, and the type of variable. So in this case, we're looking at a randomly selected child. Again, if you just wrote a child, that would be fine. I'm just going to keep emphasizing that, for good inferences, we should have samples where we randomly select things. So I'm going to keep writing in a randomly selected, but a child is just fine. And then each one of these children, the piece of information that we recorded for each of them was the age when they first walked. So we can put, walking age, or if you wanted to, age when they first walk. So how old were they when they took their first steps? And so type of variable here, again, this is measured in months. So we're looking at time, so that is quantitative and continuous. So again, when people are asked about their age, you typically would give your age to the nearest whole number, because nobody needs to know that I'm 50 years, 2 months, 3 days, 6.9 seconds old. Okay, so within there, it's good enough to just to the nearest year. Or as we're looking at babies, sometimes it moves from saying they're how many days old to weeks old to months old, and then eventually we talk about years. But again, time is on a continuous scale. So unfortunately, we're all continually getting older. As you listen to this video, by the end of the video, you will be 5 minutes older than before you listened to it. Okay, so again, time is something measured, and so is on a continuous scale. It's quantitative and continuous. All right, so part B asks for the wording of the random variable x in the context of this problem. So continuous random variables in this course will pretty much have the following general wording here. And so I am going to go up here and grab a highlighter for a second so that we can highlight that piece of information so that it's easy to flip back to in notes to find when you need it. Okay. So in the context of this problem, the measurement we were looking at was walking age, and the objects are kids or children. So this is going to be the walking age of a randomly selected child. Okay, so we've got here again the measurement of a randomly selected individual. So again, our individuals here are an individual as a child, and what we recorded, the variable information, was walking age. So in the context here, we've got the walking age of a randomly selected child. All right, so for part C, it says, why can the empirical rule be used to get approximate probabilities on this problem? And the answer here is that the empirical rule can only be used to approximate probabilities for problems where the random variable has a normal distribution. And it's given in the problem. We were told to assume the distribution is normal. So we are given assume the distribution is normal. Okay, so that's not some assumption that we just made. It was given in the problem. All right, so part D says to use the empirical rule, so we're being told to use it, to approximate the percentage of children who start walking between 12 and 18 months of age. So we're going to start with a picture from the previous page, where in that video I had commented that these percentages never change. If we have a normal distribution, these 8 percentages, those are all those approximate percentages for those probabilities in all those given 8 intervals. The thing that changes from problem to problem and with the context of the problem is what the mean and standard deviation will be. Okay, so for this one, if we go back to the previous page, they told us that mu was 15 months. Okay, they told us the mean, and the standard deviation for walking times was given as 3. Okay. Oops, I guess we could have written those right here where I put a blank for it. All right, so that means down here on this axis where mu is, that will be 15, and then the standard deviation is 3. So we're going to add 3 over and over again to the right, and we're going to subtract 3 over and over to the left. So starting at 15 and adding to the right, we'll get 18, 21, and 24. And starting back at 15 and subtracting 3 as we go to the left, we'll start at 15 and then go down to 12 and down to 9 and down to 6. All right, so now we were asked for the probability that they walk between 12 and 18 months of age. So down here on this axis, okay, here's our interval from 12 to 18, and so for a continuous random variable, that probability corresponds to the shaded area under the curve above the interval from 12 to 18. Okay, so within there we can see that the shaded region we have 34% plus another 34%, which gives us 68% altogether. So if we were to interpret this, again, we can interpret this two ways, either for an individual or percentage of all. So we can either say that there is about a 68% chance that a randomly selected child will first walk, or let's say will have a walking age between 12 and 18 months. Or we could say about 68% of all children have a walking age between 12 and 18 months. All right, so for part A, it says to use the empirical rule to approximate the percentage of children who start walking after 21 months of age. So this particular problem is a personal one to me, so to speak, because my last born son did not want to walk. He had two older sisters that basically treated him like he was a baby doll and carried him everywhere, so he just really did not need to walk. And I remember taking him into the pediatrician because our other kids had kind of walked right around a year of age, and you know, his first birthday came and went, he still wasn't walking. You know, at 15 months, still not walking. I took him in for his 18-month checkup. He still was not walking, which seemed really, really like out of the ordinary for me as a parent. And so I asked the pediatrician, and she basically said that she wasn't going to worry about it and do any intervention until 21 months. And so in my mind, I'm like, what's so special about 21 months? But it was because of the distribution of walking ages. And so again, within here, as we start into inferences, we're going to find that we're going to look at things being outside of this 2 standard deviation range as these unusual values where interventions do take place. And so the percentage of children who do start walking after 21 months of age, as we're looking at the picture, and I see here we've got a slight typo, we're going to take that extra digit 1 out of there. So we want the probability that x is to the right of 21. And so if we're looking at our picture here, to the right of 21, we've got the percentage 2.35% plus another 0.15%. And if we add those up, we get 2.5%. Okay, so again, if we put this back into the context of the problem, there is about a 2.5% chance that a child has a walking age after 21 months of age. Or again, we could say about 2.5% of all children have a walking age that's after 21 months of age. Okay, so for my youngest, Christian, he started walking right at around 21 months of age. So it's like he was paying attention at the doctor and knew, interventions were going to happen, and so he decided at 21 months of age that, maybe he should start walking. So, but again, in real world context, those means and standard deviations, there's lots of things with our human bodies that those measurements actually in these normal curves actually do explain percentages in those given intervals, and they're used to make decisions on the job.